At the physical layer of any network, transmission channels are inherently imperfect. Copper wires and fiber optics constantly pick up electromagnetic noise from their environment, and that interference can easily flip a binary 1 into a 0 during transit. To combat this, network engineers rely on redundancy. They append extra, mathematically derived bits to the original data payload. This allows the receiving machine to independently verify the structural integrity of the frame once it arrives. The simplest implementation of this concept is the single parity bit. In a system using even parity, the sender inspects the data payload prior to transmission. It then appends one extra bit to the end of the sequence, choosing either a 0 or a 1 specifically to ensure that the total count of ones in the entire frame is an even number. When that frame arrives at its destination, the receiver counts the ones. If the final sum is an odd number, it immediately knows a bit was flipped by noise, and it flags an error. But if a larger burst of noise flips exactly 2 bits simultaneously, the total number of ones remains an even number. The parity check passes, and the corrupted data slips into the system completely undetected. Furthermore, even when a single bit error is successfully caught, that solitary parity bit provides no spatial data. It alerts the receiver to the existence of an error, but it cannot identify which specific bit flipped, making any attempt at correction impossible. Because basic parity cannot locate isolated errors or survive multi-bit corruption, networks must deploy complex structural algorithms, specifically forward error correction and burst error detection, to guarantee data integrity. The objective of forward error correction is identifying the exact positional index of a corrupted bit. If the receiver knows exactly where the error occurred, it can simply invert that bit back to its original state, completely avoiding the latency penalty of requesting a retransmission from the sender. This spatial architecture relies on a strict algebraic inequality. 2 to the power of r must be greater than or equal to n plus r plus 1. Here, n represents the number of data bits, and r represents the redundant bits. To transmit a standard 7-bit ASCII character, the universal character encoding standard used to represent text in computers, our n variable equals exactly 7. To satisfy the inequality, we must introduce exactly 4 redundant bits. 7 data and 4 redundant bits create an 11-bit transmittable sequence. Redundant bits follow a strict rule, occupying powers of 2. Positions 1, 2, 4, and 8. They calculate even parity for overlapping subsets, ensuring every data bit is uniquely monitored. When an error occurs, the receiver runs a diagnostic, recalculating parities for positions 1, 2, 4, and 8 to generate a new binary sequence. This sequence translates into a base 10 integer. 0101 equals 5, proving the 5th bit is corrupted and automatically correcting it. This overlapping spatial logic, known as Hamming code, trades bandwidth by requiring a high overhead of extra bits for the sheer speed of instant, on-the-fly error correction. Sustained physical interference creates burst errors, corrupting long strings of bits all at once. This destruction easily overwhelms the localized correction capabilities of Hamming code. To detect these catastrophic burst errors, networks shift to a completely different mechanism, the cyclic redundancy check, or CRC. CRC abandons the logic of spatial bit placement entirely. Instead, it treats the entire stream of binary data as coefficients in an algebraic polynomial. A binary sequence like 10101 translates into an equation where each bit determines if a specific power of x is present. Dropping zero-value coefficients leaves a simplified generator polynomial, x to the 4th plus x squared plus 1. Before transmission begins, both the sender and the receiver must agree on one exact formula to use as their divisor, called the generator polynomial. To prepare the frame, the sender takes the original data and pads it with a string of low-order zeros. The number of zeros must equal the highest degree of the chosen generator polynomial. Then, the system executes the core computational engine of CRC, modulo 2 long division. This specific arithmetic relies on exclusive OR logic, performed entirely without arithmetic carries for addition or borrows for subtraction. This diagram shows the sender executing that modulo 2 division, dividing the padded data sequence by the generator polynomial. The ultimate output of this division is the remainder. This remainder becomes the checksum, and it physically replaces the padded zeros at the end of the frame. Appending this mathematically derived remainder creates an algebraically sealed frame. It is mathematically primed to shatter if any bits are altered during transmission. Let's shift the perspective to the destination node, which has just received this combined payload and CRC checksum from the noisy channel. The receiver has exactly one operational task. It subjects the entire incoming frame to the exact same modulo 2 division against the pre-agreed generator polynomial. This chart displays the receiver's division process, performing the XOR subtractions step by step to test the checksum. The mathematical threshold for success is absolute. If the final remainder of this division is exactly 0, the frame is mathematically proven to be error-free. Conversely, if the remainder contains any ones at all, it proves the frame suffered a burst error. The data link layer registers the failure and discards the frame entirely. CRC provides highly robust, scalable detection for massive data corruption. It prioritizes complete, guaranteed frame accuracy over the ability to correct localized errors. These two mechanisms represent completely different approaches to data integrity: the spatial overlapping logic of Hamming code versus the algebraic polynomial division of CRC. Hamming code is optimized for noisy environments where low latency is critical. It accepts a heavy bit overhead to achieve immediate forward error correction. CRC is built for high-throughput environments prone to massive burst errors. In these networks, it is computationally cheaper to accurately detect the damage, drop the frame, and trigger an automatic repeat request, or ARQ, which commands the sender to retransmit the data. Both mechanisms operate invisibly within the OSI model's 7 layers. Down at the data link layer, these algorithms intercept the incoming stream, destroy corrupted blocks, and ensure only verified data passes up to the network layer. True network reliability is not achieved by physically shielding cables from all interference, because doing so is physically impossible. Reliability is actually a mathematical illusion, engineered layer by layer through redundancy. Through the rigorous mathematics of parity checks, Hamming corrections, and CRC polynomials, the data link layer successfully translates the chaotic, noisy physical world into the flawless digital reality that modern networks depend on.